So in the meantime, I think you stressed it a lot, correct? I mean, we need low power, and I think you guys see asynchronic as the real way to get there.
Asynchronous design is one of the ways to get it, as well as reducing the leakage. So in other words, we've been focusing on high performance transistor design. But clearly, if that were not our metric and low power was our metric, for example, our chips don't need much more than 100 megahertz at best, then it opens up an entirely new technological direction where the stalling of scaling may not be your issue. And then the third thing is putting together processor and memory in an entirely different way together gives you the big, because you consume data in place rather than ferry your data long distance, right? I mean, it'd be very nice, if you grew your own food versus having to go through this entire supply chain. It's the same analogy. Moshe.
Moshe Vardi from Rice. Can you simulate any cognition by the macaque?
No. So actually, it's a very good question, and I didn't set this up, but my next slide was, what did we learn by the simulation, right? So, Moshe, to be very honest, our simulation does not think, it doesn't do, it does not see. What it allowed us to do is it allowed us to take the most optimized event-based simulation and understand the limitations of modern computing. So that was first. Then it allowed us to experiment how changing hypothesis about structure and dynamics reflects into the behavior of the simulation. So this is a purely bottom-up exercise, right? It's kind of an Indian curry being cooked by a non-Indian. You put a whole bunch of ingredients and you hope something nice will come out. It won't, right? So the counterpart of it is the top-down approach, where what you do is you can actually synthesize an algorithm or task that you want your system to do. And in fact, when you come at Alma, then I'll be able to demo to you that our chips and our smaller scale simulations can carry out tasks of perception, cognition, learning, so forth at a small scale. Now, there is a gulf between what we know from the top down and bottom up. And I'm not claiming that we understand the algorithm of the brain or that we have discovered it. That remains a challenge. But I'll tell you this. A profound realization that I had as we are going through this project is that when we were searching for brain-like function from a purely theoretical and a software and a neuroscience perspective, we were not making any progress. But when we brought in the need to design low-power, compact hardware, which sounds like everybody would say, let's figure out the algorithm first, then design the chips, right? That sounds like the rational way to do. But it turned out then the very process of incorporating technological and engineering constraints into algorithmic thinking led us to new way. And I'll tell you what the new way is. I cannot tell you what it is, but I can tell you what it should be. So in computer science, we're used to thinking in terms of algorithms. In other words, there is a problem, sort these numbers. Then you go home and you invent quick sort. That's your problem solution. You have another problem, another algorithm. We don't have ability to organically integrate this algorithm. It doesn't even make sense. What do you mean? How do you integrate sorting with hashing? What does it mean? It doesn't mean anything. But brain isn't like that. Brain is a substrate. It's an algorithm a priori of the problem. See, neither of us knew what our mother's face looked like before we were born, yet we love her as much, right? And so that ability where algorithm or the substrate comes first, and then the solution is the entire opposite way of thinking. And it's within the substrate, what kind of learning can we put? Now again, learning cannot be arbitrary. It must be local learning that we can do in hardware. So what's happened, Moshe, is that by looking at these three things together, we have narrowed we've gotten increasingly more constraints than we had before. And thus, we are making a lot more progress, which I hope to tell you long before 2018. Thanks, Moshe.
Yeah, sure. Andreas Hackerstorff, Technical University of Munich. When humans were after going the dream to fly, they were taking birds as the source of inspiration, right? And initially there were also attempts building aircrafts with flapping wings, but then engineers, they deliberately deviated from that design principle.
Absolutely.
Still there are two wings, they are in the right shape, such that with law of Bernoulli's we get lift, but there is a jet engine.
Yes, very
so
much.
my question to you is, where do you see this boundary between, on the one hand side, being inspired by natural systems, the brain, and on the other hand side, or in combination, copying elements of nature? But you can't always only copy, because this doesn't lead to a solution. Can you comment on that?
It's a very, very thoughtful question. Thank you. So I'll tell you this. So we've just finished our phase 0 and phase 1 and are commencing our phase 2. If you'd asked me these questions about 3.5 years ago, I would have told you that we were doing the former, which is just say, okay, let's make it look like a bird and see what we learn, and put together all the constraints. But now that we are so deep into the project, we have distilled from our past experience and learning a very simple specification for the chips that we are building. Conditioned on that specification, nothing else matters. So we are now clearly heading down an engineering path where we really have extracted deep insights, which I already told Leon's, in answer to Leon's question, and some to Moshe. And now our goal is quite different. So the next goal is to build about 1,000 times more powerful chip, and then to find practical applications in some sort of a real-life scenario, where, for example, one of the examples that I have here is very simple. For example, you could take one of these right brain chips and put it on a patient, right? And you could be monitoring sensors like EKG, pulse, respiration, oxygen saturation, and could be doing a real-time alert. Or imagine a grocer's glove, right? Where you have texture, smell, video, and you're just flagging bad produce. So all the places where computing couldn't go before. Or imagine taking stocks, bonds, commodities, real estate, currencies, 7/24 streaming, and you're looking for large-scale patterns to perhaps point out opportunity or risk, right? Or imagine peppering the world's water supply, the oceans, with sensors such as temperature, wave height, pressure, humidity, and that you're trying to detect tsunami or rogue wave, or trying to redirect shipping or fish traffic, so forth. So that's going to be the next challenge. It's really, I think that we have extracted it. And if we have extracted the wrong commandments, then you'll have to start a different project to correct us, because in some sense we are now on a course. And we will stay on that course to actually make these chips and to make them useful. So clearly we are moving from science to technology. But it's a very good question. And I think at this point it's more about making the airlines fuel efficient and make some, carry payload. So thanks.